Somewhere above the Earth right now, particles from the Sun are streaming through the darkness of space, traveling across 93 million miles of emptiness at speeds approaching 450 kilometers every second. This flow never stops. It has continued without pause for billions of years, and it will continue long after this moment passes. These particles, mostly electrons and protons torn from the surface of our star, carry with them the energy of solar fusion, spreading outward in all directions through the solar system. When they reach our planet, something beautiful happens. Something quiet. Something that has been happening every single night since the Earth first developed its magnetic field billions of years ago. The phenomenon we call auroras exists right now, even as you listen to these words. Somewhere on this planet, above the high latitudes near the poles, curtains of green and sometimes red and purple light are moving across the darkened sky. They are there whether anyone sees them or not. They shimmer above the Arctic ice, above the forests of Scandinavia and Alaska, above the research stations in Antarctica. They move in waves, sometimes slowly like breathing, other times more quickly, but always with a rhythm that connects directly to processes occurring far above the surface of the Earth, in the regions where our atmosphere becomes so thin that molecules are separated by vast distances, where the boundary between our world and space becomes impossible to define precisely. This is not a dramatic story. This is not a tale of conflict or urgency. This is simply an exploration of something that is happening, has always happened, and will continue to happen. The auroras are patient. They do not demand attention. They simply exist, a natural consequence of the way our sun breathes particles into space and the way our planet's magnetic field guides those particles toward the poles. If you were standing in the right place on a clear night, far enough from city lights, you would see them. You would watch as pale green light gathered along the northern or southern horizon, depending on which hemisphere held you. You would see that light intensify, perhaps form an arc that stretched from east to west across the entire span of the visible sky. And if you watched long enough, if you remained patient and still, you might see that arc begin to fold and ripple, developing vertical rays that reached upward like slow flames, moving with a grace that seems almost deliberate, though there is no consciousness behind it. Only physics. Only the interaction of energy and matter in the upper atmosphere. The journey that creates this light begins far from Earth. It begins at the Sun, where temperatures in the core reach 15 million degrees Celsius, where hydrogen atoms fuse into helium under crushing pressure, releasing energy that eventually makes its way to the solar surface and then out into space. The Sun does not hold all of its material tightly. The outer layers of the solar atmosphere, particularly a region called the corona, are hot enough and energetic enough that particles can escape entirely. They are accelerated away from the Sun by various mechanisms that scientists have studied carefully. They flow outward, and this outward flow is called the solar wind. It is not like wind on Earth. There is no air in space, no molecules bouncing into each other to create pressure differences. The solar wind is plasma, a state of matter where electrons have been stripped away from atomic nuclei, creating a mixture of charged particles that responds to magnetic fields in ways that neutral gas does not. This solar wind travels outward from the Sun in all directions at speeds that vary depending on what is happening at the solar surface. On a typical day, if we can call any solar day typical, the solar wind moves at around 250 to 750 kilometers per second. At the lower end of this range, around 250 kilometers per second, it would take these particles approximately 4 to 5 days to travel from the Sun to Earth. At the higher speeds, around 700 to 800 kilometers per second, The journey takes perhaps a day and a half. The fastest flows recorded have reached speeds near 3,000 kilometers per second, making the trip in as little as 15 to 18 hours. But these are exceptional events, connected to explosive releases of material from the Sun's surface, called coronal mass ejections. Most of the time, the solar wind moves at more moderate speeds, filling the space between the Sun and Earth with a continuous flow of charged particles that presses against the Earth's magnetic field day and night, year after year, without cease. When we speak of the Earth's magnetic field, we are describing something invisible, something that cannot be touched or seen directly, but which has profound effects on the space around our planet. Deep inside the Earth, approximately 3,000 kilometers below the surface, there is a region of liquid iron and nickel. This liquid metal moves, driven by the heat of the Earth's core and by the rotation of the planet itself. As this electrically conducting fluid moves, it generates electric currents, and these electric currents in turn generate magnetic fields. The process is called the geodynamo, and it has operated throughout most of Earth's history. The magnetic field that results from this process extends far beyond the surface of the planet, reaching out tens of thousands of kilometers into space, creating a region called the magnetosphere. The magnetosphere is not a solid structure. It is a region where the Earth's magnetic influence is stronger than the magnetic field embedded in the solar wind. The shape of this region is determined by the constant pressure of the solar wind pushing against it. On the side of Earth facing the Sun, the magnetosphere is compressed, pushed inward by the solar wind until the pressures balance at a boundary about 10 Earth radii away from the planet's center, or roughly 60,000 kilometers from the surface. On the night side of Earth, away from the Sun, the solar wind stretches the magnetosphere out into a long tail that extends more than 200 Earth radii into space, perhaps 1,000,000 kilometers or more. This tail looks somewhat like the tail of a comet, though it is made not of dust and gas, but of magnetic field lines and trapped plasma. The magnetic field lines themselves can be visualized as invisible pathways that emerge from one magnetic pole, arc through space, and return to the other magnetic pole. These are not physical objects. They are simply a way of mapping the direction and strength of the magnetic field at any point in space. But they are useful for understanding how charged particles move, because charged particles do not move in straight lines through a magnetic field. They spiral along the field lines, following these invisible pathways as they travel through space. Near the equator, far from the poles, the magnetic field lines run roughly parallel to the Earth's surface, extending far out into space before curving back. But near the poles, the field lines are nearly vertical, emerging from the ground and extending upward into space. It is this geometry, this funnel shape of the magnetic field near the poles, that directs solar wind particles down into the upper atmosphere. Not all solar wind particles enter the magnetosphere. Most are deflected, swept around the Earth by the magnetic field, and carried away downstream. But some particles, particularly when the conditions are right, can enter the magnetosphere and become trapped. They spiral along the field lines, bouncing back and forth between the northern and southern hemispheres, sometimes for hours or days, stored in regions of the magnetosphere like invisible reservoirs of energy. And some of these particles, under the right conditions, are accelerated down the magnetic field lines toward the Earth, particularly near the poles. As they descend toward the planet, they maintain their spiraling motion, but they also travel along the field line, moving closer and closer to the surface until finally they enter the upper atmosphere. The atmosphere at these altitudes is not like the atmosphere at ground level. At sea level, the air is dense, with molecules packed closely together, colliding with each other billions of times per second. But at altitudes above 100 kilometers, the atmosphere becomes progressively thinner. The number of molecules in any given volume of space decreases exponentially with altitude. At 100 kilometers above the Earth's surface, the atmospheric density is already less than 1/1,000,000th of what it is at sea level. At 200 kilometers, it is less than 1/1000,000th. The molecules that remain are spread so thinly through space that they rarely collide with each other. This is the region where auroras form, in the thin upper reaches of the atmosphere, where the boundary between air and space becomes blurred. When energetic particles from the magnetosphere descend into this region, they collide with the atoms and molecules that are present. The most common atmospheric components at these altitudes are molecular nitrogen, which makes up most of the lower atmosphere, and atomic oxygen. Molecular nitrogen consists of two nitrogen atoms bonded together. At lower altitudes in the atmosphere, oxygen also exists primarily in molecular form, two oxygen atoms bonded together, the form that we breathe. But at altitudes above about 90 kilometers, ultraviolet radiation from the sun splits oxygen molecules apart, creating atomic oxygen. During the night, when there is no sunlight to continue this process, the oxygen atoms can persist for long periods without recombining because the atmosphere is so thin that atoms rarely encounter each other. This atomic oxygen becomes a major component of the upper atmosphere, and it plays a central role in creating the most common color of the aurora. The colors we see in auroras come from a process that scientists call excitation and emission. When a fast-moving electron from the magnetosphere collides with an oxygen atom or nitrogen molecule in the upper atmosphere, it can transfer some of its energy to that atom or molecule. This energy kicks one of the atom's electrons into a higher energy state, a configuration that is not stable. The atom does not remain in this excited state indefinitely. After a period of time, the electron falls back to a lower energy level, and when it does, it releases the extra energy in the form of light. The color of that light, the wavelength of the electromagnetic radiation that is emitted, depends on exactly which energy transition is occurring. Different atoms and different excited states produce different colors. The most common auroral color is green, a particular shade of green with a wavelength of 557.7 nanometers. This green light comes from atomic oxygen that has been excited to a particular energy state. When an oxygen atom absorbs energy from a collision with an energetic particle, one of its electrons can be kicked into this excited state, and approximately 7/10 of a second later, on average, the electron falls back down, emitting a green photon. 7/10 of a second is not long in human terms, but in the world of atomic processes, it is actually quite slow. It is slow enough that if the oxygen atom collides with another atom or molecule before it has a chance to emit its photon, the extra energy can be transferred away through the collision instead, a process called collisional quenching. This means that green oxygen emission can only occur at altitudes where the atmosphere is thin enough that collisions are infrequent enough to allow the oxygen atoms time to emit their light. Below about 95 kilometers in altitude, the atmosphere becomes dense enough that most oxygen atoms in this excited state lose their energy through collisions before they can emit light. This sets a lower boundary for the green aurora. The green light we see typically comes from altitudes between about 100 and 250 kilometers above the Earth's surface. At higher altitudes, where the atmosphere is even thinner, another form of oxygen emission becomes possible. This emission produces red light with a wavelength of 630 nanometers. It comes from oxygen atoms excited to a different energy state, one with an extraordinarily long lifetime. On average, an oxygen atom in this state will remain excited for about 100 seconds, almost 2 minutes, before emitting its red photon. This is an eternity in atomic terms. During those 100 seconds, the oxygen atom can travel large distances, carried by winds in the upper atmosphere or simply drifting through space. It can move through regions where the auroral activity is no longer present, which is why red auroras appear more diffuse than green ones, less structured, washed out compared to the sharp rays and curtains seen in the green emissions. And because of this long lifetime, collisional quenching is even more effective at suppressing red emission. Only at altitudes above about 200 or even 300 kilometers, where the atmosphere is thin enough that oxygen atoms can go for minutes without colliding with anything, does this red emission become visible. When we see red in an aurora, particularly above the green emissions, we are seeing light that comes from the highest altitudes where auroral processes occur. Below the green, sometimes, a different color appears. When solar activity is particularly intense, when the particles bombarding the atmosphere are carrying especially high energies, they can penetrate deeper into the atmosphere, down to altitudes where oxygen emission becomes quenched and molecular nitrogen takes over. Molecular nitrogen produces emissions in the blue and red parts of the spectrum. The blue emissions have very short lifetimes, essentially instantaneous by atomic standards. The nitrogen molecule absorbs energy and immediately emits light without any significant delay. These prompt emissions can survive even at lower altitudes, down to perhaps 80 or 90 kilometers, because there is no long-lived excited state to be quenched by collisions. When blue or purple appears at the bottom edge of an auroral curtain, it often indicates that the aurora is being driven by particularly energetic particles. The deep red that sometimes appears, also from nitrogen, adds to the complex palette of colors that auroras can display. These reds from nitrogen are different from the pale reds of high-altitude oxygen, more saturated, sometimes appearing almost crimson. The colors mix in various combinations depending on the altitude, the energy of the incoming particles, and the composition of the atmosphere at the location where the emissions occur. Green is almost always present during an auroral display of any significant brightness, because the atmospheric conditions at the altitudes where green oxygen emission occurs are nearly always suitable for auroral processes. Red, from high-altitude oxygen, appears primarily during very active displays, when the auroral activity extends to high altitudes and when the energetic particles are numerous enough to excite oxygen atoms even in the very thin upper atmosphere. Blue and purple from nitrogen appear primarily at the lower edges of very active auroras, when high-energy particles penetrate deep into the atmosphere. Sometimes all these colors are present simultaneously at different altitudes, creating auroras that display green in the middle sections, red at the top, and blue or purple at the bottom. Sometimes the colors are more uniform. The variability is part of the nature of the phenomenon, connected to the constantly changing conditions in the magnetosphere and the solar wind. The auroras do not appear randomly scattered across the sky. They form in a specific pattern, a ring-shaped region centered on each magnetic pole of the Earth. This ring is called the auroral oval. It is not centered on the geographic poles, the points where the Earth's rotation axis intersects the surface, but rather on the magnetic poles, which are offset from the geographic poles by about 10 or 11 degrees. The North Magnetic Pole is currently located in northern Canada, and the South Magnetic Pole is in Antarctica but offset from the geographic South Pole. The auroral oval is an ellipse displaced by the solar wind. On the day side, the side facing the sun, the oval is typically located at about 75 degrees magnetic latitude, quite far from the pole. On the night side, away from the sun, the oval extends down to about 67 degrees magnetic latitude, closer to the equator. This displacement is caused by the pressure of the solar wind, which compresses the magnetosphere on the sunward side and stretches it out on the night side. The auroral oval exists continuously. Even during periods of very low solar activity, even when the solar wind is weak and slow, there is still an auroral oval. During these quiet times, the oval is narrow, perhaps 5 or 6 degrees wide in latitude, and it stays close to the magnetic poles. The aurora it contains is faint, often appearing as simple arcs that stretch from east to west across the sky without much structure or brightness. But it is there, a persistent ring of light encircling each magnetic pole. As geomagnetic activity increases, as the solar wind strengthens or becomes more variable, the auroral oval expands. It grows wider and moves toward the equator, particularly on the night side. During strong geomagnetic storms, the kind that occur when fast coronal mass ejections from the sun strike the Earth's magnetosphere, the auroral oval can expand to mid-latitudes, bringing auroras to regions that normally never see them. Auroras have been reported as far south as the Mediterranean, as far south as Cuba and Hawaii in the northern hemisphere, and equivalently far north in the southern hemisphere during the strongest storms. But these are exceptional events. Most of the time, the auroral oval remains at high latitudes, visible only from regions near the Arctic or Antarctic circles. The oval is a mirror image in both hemispheres. When aurora activity increases in the north, it increases simultaneously in the south. The northern lights, aurora borealis, and the southern lights, aurora australis, are created by the same processes and occur at the same time, driven by the same solar wind conditions. If you could observe both poles simultaneously from space, you would see the two auroral ovals, expanding and contracting together, brightening and dimming in unison, responding to changes in the magnetosphere that affect both poles equally. The symmetry is not perfect. Sometimes local conditions can cause differences in the exact patterns, and the structure of the Earth's magnetic field is not perfectly symmetrical. But the overall behavior is coupled, a consequence of the fact that magnetic field lines connect the two hemispheres, and particles that spiral along these field lines bounce back and forth between north and south. The location of the auroral oval moves with the Earth's magnetic field orientation relative to the Sun, but it does not rotate with the planet in the simple way you might expect. Instead, it maintains a roughly fixed orientation with respect to the Sun-Earth line. As the Earth rotates beneath it, different locations pass through the oval. This is why auroras are most commonly seen around local midnight at any given location in the auroral zone. The midnight sector of the oval is the most active region, where auroras are brightest and most dynamic. As a location rotates through this midnight sector, someone standing there would see the aurora appear in the northern sky, grow brighter and more active, and then fade as the location continues to rotate through the oval and out the other side. This gives auroral displays a characteristic time structure, with activity building during the late evening, reaching a peak around midnight or slightly later, and then declining in the early morning hours. Within the auroral oval, the aurora itself takes various forms. During quiet conditions, as mentioned, simple arcs are common. These arcs can extend from one horizon to the other, thin bands of light that remain relatively stable for long periods. But as activity increases, the arcs begin to develop structure. Vertical rays appear, columns of light that seem to hang down from the arcs like curtains or draperies. The arcs can split into multiple parallel structures. Waves can develop along the arcs, traveling from east to west or west to east. The aurora can begin to move more rapidly, the curtains swaying and folding, the rays brightening and fading. During the most active periods, the entire sky can fill with light, with multiple arcs and rays appearing simultaneously at different locations, creating a complex, shifting display that can cover the entire visible sky from horizon to horizon. The mechanisms that create these forms and this movement are connected to processes occurring in the magnetosphere far above the visible aurora. The particles that create the light we see have been accelerated down the magnetic field lines by electromagnetic processes in the near-Earth space environment. One important process involves waves in the Earth's magnetic field, called Alfvén waves. These are waves that propagate along magnetic field lines, carrying energy and momentum. When conditions are right, these waves can accelerate electrons to very high speeds, directing them down toward the atmosphere. The electrons effectively surf on the waves, gaining energy as they travel. When they enter the atmosphere, they have enough energy to excite and ionize atmospheric atoms and molecules, creating the auroral light. The speed and energy of these electrons determine how deep into the atmosphere they can penetrate before they lose their energy through collisions. Low-energy electrons, traveling at perhaps a few thousand kilometers per second, will be stopped at high altitudes, above 200 kilometers, where they will primarily excite oxygen to the red-emitting state. Higher-energy electrons, traveling at a significant fraction of the speed of light, can penetrate much deeper, down to 90 or 100 kilometers, or even lower, where they can excite oxygen to the green-emitting state and excite nitrogen molecules to produce blue and purple emissions. The energy distribution of the electrons is not constant. It varies with the level of geomagnetic activity and with the specific processes occurring in the magnetosphere at any given time. This is why the color distribution in auroras changes during a display, with the relative amounts of red, green, blue, and purple shifting as conditions in the magnetosphere evolve. The aurora is not the only effect of these particles entering the atmosphere. They also create electric currents in the upper atmosphere, flowing along the auroral oval in the east-west direction. These currents are called auroral electrojets, and they involve the flow of millions of amperes of current through the ionosphere. The currents interact with the Earth's magnetic field, creating detectable variations in the magnetic field strength measured on the ground. Sensitive magnetometers located at high latitudes can detect these variations, and they are used to monitor auroral activity and geomagnetic conditions. The strength of the magnetic variations is correlated with the brightness and intensity of the aurora, with larger currents producing both brighter auroras and stronger magnetic disturbances. The energy deposited into the upper atmosphere by auroral particles is substantial. During active auroral displays, the total power deposited can reach hundreds of gigawatts, comparable to the total power consumption of human civilization. But the atmosphere is vast, and this energy is spread out over large areas, so the effects at any one location are not overwhelming. The primary effect is heating of the upper atmosphere. The energy transferred from the particles to the atmospheric atoms and molecules appears initially as light and as kinetic energy of the atoms and molecules. This kinetic energy manifests as temperature, making the upper atmosphere warmer during auroral activity. The temperature increase can be hundreds of degrees Celsius in the thermosphere, the atmospheric region above about 80 kilometers. But the air is so thin at these altitudes that, despite the high temperature, there is very little total heat energy per unit volume. A person floating in the thermosphere during an aurora would not feel warm because there are too few molecules to transfer significant heat to the body. Some of the energy also drives winds in the upper atmosphere. The heating creates pressure differences, and these pressure differences drive the movement of air. At auroral altitudes, these winds can reach speeds of hundreds of meters per second, far faster than winds in the lower atmosphere. The winds can transport atmospheric constituents from one region to another, affecting the composition of the upper atmosphere. They can also interact with the electric currents and magnetic fields, creating complex feedback effects that influence the evolution of the auroral display. The continuous nature of auroral activity means that these effects on the upper atmosphere are ongoing. Even during geomagnetically quiet times, when auroras are faint and confined to high latitudes, there is still energy being deposited, still heating occurring, still electric currents flowing. The upper atmosphere at high latitudes is constantly being influenced by the connection between the Earth and the Sun, by the flow of energy from the solar wind through the magnetosphere and into the atmosphere. This has been true throughout Earth's history, since the magnetic field first developed billions of years ago. The aurora has been present, in one form or another, for eons, a constant feature of the Earth's interaction with its space environment. The variability in auroral activity is driven primarily by variability in the solar wind. The Sun is not a static object. Its surface is dynamic, with magnetic fields twisting and reorganizing, with regions of intense magnetic activity called sunspots appearing and disappearing over the course of days and weeks. The solar wind that emerges from the Sun reflects this variability. Sometimes, the wind is relatively steady and slow, flowing from the polar regions of the Sun's corona through large coronal holes, regions where the magnetic field opens up and allows material to stream outward. At other times, the wind is disturbed by dramatic events on the solar surface. These events include solar flares, sudden releases of energy caused by magnetic reconnection in the Sun's atmosphere, and coronal mass ejections. Coronal mass ejections, sometimes abbreviated as CMEs, are particularly important for auroral activity. A coronal mass ejection is a large-scale expulsion of plasma and magnetic field from the Sun's corona. During a CME, billions of tons of material are thrown outward from the Sun, accelerated to speeds that can exceed 1,000 kilometers per second. The material travels through interplanetary space, expanding as it goes, and if the CME is directed toward Earth, it will eventually reach our planet. The travel time depends on the speed of the ejection. Slow CMEs, moving at 250 to 400 kilometers per second, can take 3 to 5 days to reach Earth. Fast CMEs, moving at 2,000 or 3,000 kilometers per second, can arrive in as little as 15 to 18 hours. When a CME arrives at Earth, it compresses the magnetosphere, sometimes quite dramatically. The pressure of the solar wind increases, and if the magnetic field embedded in the CME happens to be oriented opposite to the Earth's magnetic field, conditions become favorable for magnetic reconnection at the boundary of the magnetosphere. Magnetic reconnection is a process where magnetic field lines from the solar wind and from the Earth's magnetosphere merge and then break apart in a new configuration, allowing energy and particles from the solar wind to enter the magnetosphere much more efficiently than usual. The result is a geomagnetic storm, a period of enhanced auroral activity that can last for hours or even days. During a geomagnetic storm, driven by a CME, the auroral oval expands dramatically. Auroras that are normally confined to latitudes above 65 or 70 degrees can extend down to 50 degrees, 40 degrees, even 30 degrees during the most intense storms. The auroras become much brighter, transitioning from faint glows to brilliant displays that can illuminate the landscape. The colors become more varied, with red becoming more prominent as high-energy particles penetrate to very high altitudes and excite oxygen in the rarefied upper atmosphere. The motion becomes more rapid and more dramatic, with curtains and rays sweeping across the sky in waves, sometimes moving from one horizon to the other in just a few tens of seconds. The largest geomagnetic storms in recorded history have been caused by CMEs. The most famous is the Carrington event, which occurred in September 1859. During this event, auroras were seen as far south as the Caribbean and Hawaii in the northern hemisphere, and as far north as central Chile in the southern hemisphere. The geomagnetic disturbances were so strong that telegraph systems, the most advanced electrical technology of the time, were disrupted. Telegraph operators reported receiving electrical shocks, and some telegraph lines could be operated using only the electrical currents induced by the geomagnetic storm without any need for batteries. The storm was caused by an exceptionally fast CME, one that reached Earth in about 17 hours after being launched from the Sun by a powerful solar flare. Modern analysis of the magnetic records from that time suggests that the storm was among the most intense ever recorded, with disturbances in the Earth's magnetic field reaching magnitudes rarely seen before or since. Events like the Carrington event are rare. Studies of solar activity suggest that CMEs strong enough to cause such intense geomagnetic storms occur perhaps once every few centuries, but smaller storms are more common. Storms strong enough to bring auroras to mid-latitudes, say to the northern United States or Central Europe, might occur several times per solar cycle. A solar cycle is the approximately 11-year period over which solar activity waxes and wanes. During solar maximum, the peak of the cycle, the Sun is more active with more sunspots, more solar flares, and more CMEs. During solar minimum, the Sun is quieter, though not completely inactive. The variability in solar activity over the solar cycle means that auroral activity also varies, with more frequent and more intense displays occurring during and shortly after solar maximum. But auroras are not confined to Earth. Other planets with magnetic fields and atmospheres also have auroras. Jupiter, the largest planet in the solar system, has auroras that are far more powerful than those on Earth. Jupiter's magnetic field is much stronger than Earth's, about 14 times stronger at the equator, and its magnetosphere is correspondingly larger, extending to distances of several million kilometers from the planet. The auroras on Jupiter are driven partly by the solar wind, but they also have a unique contribution from Jupiter's volcanic moon, Io. Io orbits very close to Jupiter, and its volcanoes spew enormous amounts of sulfur dioxide and other gases into space. These gases become ionized by Jupiter's magnetic field and form a torus, a donut-shaped ring of plasma that orbits the planet along with Io. This plasma interacts with Jupiter's magnetic field and magnetosphere, creating electric currents that accelerate particles down into Jupiter's atmosphere, generating auroras that are visible continuously even when solar wind conditions are quiet. The auroras on Jupiter are bright enough that they can be observed from Earth-based telescopes, particularly in ultraviolet light, and spacecraft visiting Jupiter have returned spectacular images showing the auroral ovals at Jupiter's north and south poles, glowing, brilliantly against the darkness of the planet's polar regions. Saturn also has auroras, though they are less intense than Jupiter's. Saturn's magnetic field is weaker than Jupiter's, and its magnetosphere is correspondingly smaller. The auroras on Saturn are also driven by a combination of solar wind and internal processes. One of Saturn's moons, Enceladus, has geysers that spray water vapor into space, and this water becomes ionized and contributes to Saturn's magnetosphere, much like Io's contribution to Jupiter's. The auroras on Saturn have been observed by spacecraft, including the Hubble Space Telescope and the Cassini mission, which orbited Saturn for 13 years. The auroral displays on Saturn are more variable than those on Jupiter, responding more directly to changes in the solar wind. Uranus and Neptune, the ice giants of the outer solar system, also have magnetic fields and auroras, though much less is known about them because these planets are so far from Earth and have been visited by spacecraft only briefly. Voyager 2 flew past Uranus in 1986 and past Neptune in 1989, and during those flybys it detected auroral emissions from both planets. The magnetic fields of Uranus and Neptune are unusual, tilted at large angles relative to their rotation axes and offset from their centers, which gives their magnetospheres complex and asymmetric shapes. This likely affects the auroras, making them different in character from those on Earth or the gas giants, but the details remain uncertain. Even Mars, which does not have a global magnetic field like Earth, has auroras of a sort. Mars lost its global magnetic field billions of years ago, but there are localized regions of crustal magnetism, areas where rocks in the Martian crust are magnetized and create small-scale magnetic fields. When solar wind particles interact with these localized magnetic fields, they can be channeled down to the Martian atmosphere, creating auroras. These Martian auroras are different from those on Earth. They occur at lower latitudes, sometimes appearing over regions where the crustal magnetic field is strong, and they are more diffuse and less structured than Earth's auroras. The auroras on Mars were first detected by instruments on the Mars Express spacecraft in 2004, and later observations from NASA's MAVEN mission have provided more details about their occurrence and characteristics. Even more exotic are auroras on other solar system bodies. Venus, which like Mars has no global magnetic field, nonetheless can have auroras. These are created when solar wind particles interact directly with the upper atmosphere on the night side of the planet. The interactions create localized glows, though these are quite different from the structured auroral ovals seen on magnetized planets. And in 2015, astronomers reported the first detection of auroras beyond the solar system on a brown dwarf star about 18 light-years from Earth. This brown dwarf, a failed star that is too small to sustain hydrogen fusion like a true star, has a strong magnetic field and is surrounded by charged particles, and it displays auroral emissions that are detected at radio wavelengths. The discovery suggests that auroras might be a common phenomenon wherever there are magnetic fields and atmospheres, extending the reach of this beautiful process far beyond our own planet. Back on Earth, there is another aspect of auroras that has intrigued people for centuries, and that is the question of whether auroras make sound. There are numerous historical reports from people living at high latitudes describing faint sounds that accompany particularly intense auroral displays. The sounds are typically described as crackling, hissing, rustling, or popping noises, very quiet and difficult to hear, occurring synchronously with rapid movements in the aurora overhead. For most of the 20th century, these Reports were dismissed by scientists as folklore or as auditory illusions. The reasoning was simple. The aurora occurs at altitudes of 100 kilometers or more, and sound cannot travel such distances through the atmosphere. At the speed of sound in air, which is about 340 meters per second, it would take over 5 minutes for sound to travel from an altitude of 100 kilometers down to the ground. But the sounds people reported occurred simultaneously with changes in the aurora, with no delay. This suggested that if the sounds were real, they could not be coming from the aurora itself. Research over the past few decades has begun to shed light on this mystery. In 2012, a researcher from Aalto University in Finland named Untu Lane reported that he had successfully recorded sounds that appeared to be correlated with auroral activity. The sounds were recorded during a geomagnetic storm, using microphones positioned at ground level, and they consisted of faint clapping or popping sounds that occurred during periods of rapid changes in the Earth's magnetic field. Lane proposed that the sounds were not coming from the aurora itself, but rather from electrical discharges in a thin layer of air much closer to the ground. The mechanism Lane proposed involves temperature inversions. A temperature inversion is a layer in the atmosphere where temperature increases with altitude rather than decreasing, as it normally does in the lower atmosphere. These inversions often form near the ground during cold, calm nights, which are exactly the conditions when auroras are most commonly observed at high latitudes. The inversion layer can trap charged particles near the ground, creating a layer where electric charge accumulates. During a geomagnetic storm, when the Earth's magnetic field is changing rapidly, these changes can induce electric fields that cause the accumulated charge to discharge, creating tiny sparks or electrical breakdown events in the air. These events would produce faint crackling sounds at ground level, and they would occur simultaneously with changes in the aurora overhead, because both are responding to the same geomagnetic disturbances. This explanation remains somewhat speculative. The phenomenon is rare and difficult to study, requiring both intense auroral activity and the right atmospheric conditions at ground level. Most auroral displays do not produce any audible sound, and even during intense storms, the sounds are reported by only a small fraction of observers. The majority of auroral observations remain entirely silent experiences, with the light moving soundlessly across the sky. But the possibility that certain auroral displays can create sounds, even if indirectly, adds another dimension to the phenomenon. A reminder that auroras are not just visual displays, but complex interactions between the sun, the magnetosphere, the atmosphere, and the ground. The study of auroras has a long history stretching back centuries. The name Aurora Borealis was coined by the astronomer Galileo Galilei in 1619, combining the name of the Roman goddess of dawn, Aurora, with the Greek god of the north wind, Boreas. The term Aurora Australis for the southern lights came later, using the Latin word for south. But humans have observed and wondered about auroras for far longer than scientific names have existed. Archaeological and historical records show that auroras were noted by cultures around the world. The ancient Chinese recorded observations of auroral-like phenomena as early as 2,500 years ago. Indigenous peoples in the Arctic regions of North America, Scandinavia, and Russia have countless stories and legends about the lights in the sky. Some saw them as the spirits of the dead, others as omens or messages from the gods, still others as natural phenomena connected to the weather or the seasons. Scientific understanding of auroras began to develop in earnest during the 18th and 19th centuries, as instruments became available to measure magnetic fields, and as communication networks made it possible to correlate observations from different locations. In the 1830s, the scientist Carl Friedrich Gauss developed mathematical techniques for analyzing the Earth's magnetic field and established a network of magnetic observatories around the world. His work laid the foundation for understanding the connection between auroras and geomagnetic disturbances. In the late 1800s, the Norwegian physicist Christian Birkeland conducted pioneering experiments and observations that demonstrated the connection between auroras and electric currents flowing in the upper atmosphere. Birkeland also proposed, correctly, that the particles creating the aurora came from the sun, though he did not yet have the understanding of the solar wind that would develop later. The modern understanding of auroras came together during the 20th century, particularly after World War II, as rockets and satellites made it possible to measure conditions in the upper atmosphere and in space directly. In 1958, the Explorer satellites discovered the Van Allen radiation belts, regions of space around Earth where energetic particles are trapped by the magnetic field. This discovery revealed that the magnetosphere was a complex and dynamic environment, with particles being stored and released in ways that had not been anticipated. Throughout the 1960s and 70s, a series of satellites and sounding rockets provided increasingly detailed measurements of the aurora, its altitude, its spectrum, the energy of the particles creating it, and its relationship to the magnetosphere. By the end of the 20th century, the basic physical processes creating auroras were well understood, though many details continue to be active areas of research. Today, auroras are monitored continuously by networks of cameras and magnetometers on the ground and by satellites in space. The data from these observations are used not just for scientific research, but also for practical purposes. Geomagnetic storms that produce auroras can also disrupt technology. The electric currents flowing in the ionosphere during storms can induce currents in long conductors on the ground, including power transmission lines, pipelines, and telecommunication cables. In severe cases, these induced currents can damage transformers and other equipment, leading to power outages. The most famous example occurred in March 1989, when a geomagnetic storm caused a power blackout in Quebec that left 6 million people without electricity for 9 hours. Satellite systems can also be affected, as the increased density and temperature of the upper atmosphere during storms causes increased drag on satellites in low Earth orbit, and the energetic particles can damage satellite electronics. Because of these impacts, space weather forecasting has become an important activity, and agencies around the world, including NOAA in the United States and similar organizations in other countries, issue forecasts and warnings of geomagnetic storms based on observations of the sun and the solar wind. But for most people, auroras remain primarily a source of wonder and beauty. The experience of standing under an aurora is unlike anything else. The vastness of the sky, the silence of a winter night, the slow, graceful movement of light across the darkness, all combine to create a sense of connection to something much larger than ourselves. There is a quietness to the experience that is difficult to describe. Even when the aurora is bright and active, even when curtains of light are sweeping overhead, there is no sound, no rush of wind, nothing but the visual display. The light itself is gentle. It does not hurt the eyes the way bright artificial lights do. It is possible to watch an aurora for hours without discomfort, simply standing or sitting, wrapped in warm clothes against the cold, looking up. The colors have a quality that is difficult to photograph. Cameras can capture the aurora, and modern digital cameras are sensitive enough to record auroras that are too faint for the eye to see. But cameras render the colors differently than the human eye does. To the naked eye, auroras often appear primarily white or pale green, with other colors visible only during particularly bright displays. This is because the human eye has two types of light receptors: rods, which are very sensitive but cannot distinguish colors well, and cones, which can see color but require more light. During a typical auroral display, the light is bright enough to activate the rods, but not quite bright enough to fully activate the cones. So the eye sees the aurora but perceives it as relatively colorless. Cameras, on the other hand, can integrate light over several seconds or longer, building up enough signal to bring out the colors vividly. This is why photographs of auroras often show brilliant greens, reds, and purples, while someone who was present might report that the aurora appeared pale and ghostly. Neither perception is wrong. They are simply different ways of recording the same phenomenon. The movement of auroras is one of their most captivating features. During active displays, the curtains and rays move continuously, swaying and folding, sometimes slowly and sometimes more rapidly. The motion is not random. It follows patterns that reflect the underlying physics of the processes occurring in the magnetosphere and atmosphere. Alphen waves traveling along magnetic field lines create traveling features in the aurora, waves of brightening that move along auroral arcs at speeds of several kilometers per second. The curtains themselves can pulse, brightening and dimming with periods of a few seconds or tens of seconds, driven by oscillations in the electrical currents and particle fluxes. Sometimes the entire auroral display will suddenly intensify, a phenomenon called an auroral substorm. During a substorm, the aurora brightens dramatically, often beginning in one region of the sky and then spreading rapidly across the entire auroral oval. The curtains become more structured, with rays reaching high overhead. The display lasts for tens of minutes to a few hours and then gradually fades as the magnetosphere relaxes. These substorms are one of the most dramatic manifestations of the dynamic nature of the magnetosphere. They occur when energy that has been gradually accumulated in the magnetosphere is suddenly released, accelerating particles down into the atmosphere in a burst of activity. The energy for substorms comes from the solar wind, but it is stored in the magnetosphere's magnetic field, in the stretched-out tail on the night side of the Earth. When conditions are right, the magnetic field in the tail becomes unstable and snaps back toward a more relaxed configuration, a process that involves magnetic reconnection and the rapid conversion of magnetic energy into kinetic energy of particles. The result is a substorm, visible from the ground as a sudden intensification of the aurora. For all the complexity of the physics involved, the end result is something that appears almost organic. The movement of auroral curtains looks like slow flames, or like ripples moving through fabric, or like the surface of water disturbed by wind. There is a grace to the motion that seems almost deliberate, though of course there is no consciousness directing it, only the interplay of electromagnetic forces and particles. This quality of the aurora, this sense of watching something alive, is part of what makes it so mesmerizing. It is easy to lose track of time while watching an aurora, to stand for hours as the display evolves, forgetting the cold, forgetting everything else except the light moving across the sky. The best auroras occur during dark, moonless nights, when the sky is clear and there is no light pollution. The moon, when it is bright, can wash out fainter auroras, and city lights make it difficult to see all but the most intense displays. This is why auroras are most easily seen from remote locations at high latitudes, far from urban areas. Many people travel to places like northern Norway, Iceland, Alaska, or northern Canada specifically to see the aurora. There is a small industry that has grown up around aurora tourism, with guides who monitor forecasts and take visitors to dark locations when auroras are expected. But auroras do not always cooperate with schedules. They are driven by processes on the sun that are difficult to predict more than a few days in advance, and even when conditions are favorable, clouds can obscure the sky. Seeing a truly spectacular auroral display requires patience, luck, and a willingness to spend hours outside in the cold, waiting and watching. There is also a meditative quality to aurora watching. The act of standing outside in the darkness, looking up at the sky, waiting for something to happen, requires a kind of patience and presence that is increasingly rare in modern life. There is nowhere to rush to, nothing to check or update or respond to. There is only the sky and the possibility of light. And when the light appears, it unfolds on its own schedule, at its own pace. You cannot make it move faster or slower. You cannot control it or direct it. You can only watch, and in watching, become part of the experience. The aurora connects us to the sun in a direct and tangible way. The light we see is the result of particles that left the sun days ago, traveling across 93 million miles of space, guided by magnetic fields, funneled down into the atmosphere, colliding with oxygen and nitrogen atoms. Every auroral display is evidence of the sun's influence on the Earth, a reminder that we live not on an isolated planet, but within the extended atmosphere of a star. The solar wind that creates auroras also shapes the magnetosphere, protects the Earth from some forms of cosmic radiation, and influences the chemistry of the upper atmosphere. The sun's magnetic field, which extends throughout the solar system in the form of the interplanetary magnetic field carried by the solar wind, connects all the planets in a web of electromagnetic interactions. The aurora is one visible manifestation of this connection, a window into processes that are usually invisible. It is worth considering the timescales involved in auroral processes. The particles that create the aurora are traveling at speeds of thousands or tens of thousands of kilometers per second when they enter the atmosphere. They collide with atmospheric atoms within a tiny fraction of a second after arriving. The excited oxygen and nitrogen atoms emit their light on timescales ranging from nanoseconds to seconds or even minutes, depending on which emission is involved. But the processes that created those particles, that accelerated them in the magnetosphere, that launched them from the sun, occur on timescales of minutes to hours to days. And the solar magnetic activity that ultimately drives all of this varies on timescales of weeks, years, and the 11-year solar cycle. The aurora is a nexus where all these timescales intersect, where the fast and the slow, the immediate and the long-term, come together in a single phenomenon. The Earth's magnetic field itself, which is essential for the existence of auroras as we know them, operates on even longer timescales. The geodynamo that generates the field has been operating for billions of years, and it will continue to operate for billions more as long as the Earth's core remains liquid and in motion. But the field is not constant. It varies in strength and orientation over timescales of decades to millennia. The magnetic poles drift, moving slowly across the surface of the Earth. Over longer periods, the entire magnetic field can reverse, with the north and south magnetic poles switching places. These reversals have occurred hundreds of times in Earth's history, at irregular intervals averaging a few 100,000 years. During a reversal, which might take several thousand years to complete, the magnetic field becomes more complex and weaker, and the location and character of auroras would change. But between reversals, the field is relatively stable and the auroras continue in their familiar patterns, ovals of light encircling the magnetic poles, driven by the solar wind, a constant feature of the Earth's interaction with space. As we think about auroras in this way, as part of a vast system of electromagnetic interactions connecting the Sun and Earth and extending across the solar system, it becomes clear that what we see in the sky is only the visible tip of a much larger phenomenon. The aurora is the place where space weather becomes visible, where abstract concepts like magnetic reconnection and plasma physics and charged particle dynamics manifest as light and color and motion. It is a reminder that the apparently empty space around our planet is not empty at all, but filled with particles and fields and energy, constantly in motion, constantly interacting. There is something deeply calming about this perspective. The processes that create auroras have been occurring for billions of years. They will continue for billions more. The solar wind flows, the magnetic field channels it toward the poles. Particles collide with the atmosphere, light is emitted. Night after night, year after year, millennium after millennium. Human civilizations have risen and fallen, entire species have evolved and gone extinct, continents have drifted across the surface of the planet, and through it all, the aurora has been there, a constant presence in the polar skies. Knowing this, standing under an aurora and watching the light move. Across the sky, there is a sense of being connected to something that transcends the immediate moment, something that links the present to the deep past and the distant future. For those who have never seen an aurora, it might seem strange to describe such a phenomenon as relaxing. Light in the sky, movement, color, these might seem like things that would be stimulating rather than calming. But there is a quality to the aurora that is fundamentally peaceful. Perhaps it is the silence, the complete absence of sound despite the visual activity. Perhaps it is the slow, gentle motion, which is active enough to hold attention, but not so rapid or violent as to be alarming. Perhaps it is simply the beauty of it, the fact that the colors and forms are so intrinsically pleasing to look at. Or perhaps it is the knowledge that this is a natural phenomenon, driven by forces far beyond human scale, utterly indifferent to human concerns, a reminder of the universe's vastness and our small place within it. Whatever the reason, many people report that watching an aurora is a meditative experience, one that quiets the mind and brings a sense of peace. This quality of the aurora has been recognized in different ways by different cultures. Some indigenous traditions in the Arctic speak of the aurora as a bridge between worlds, a place where the boundary between earth and sky, between the physical and the spiritual, becomes thin. While modern science describes the aurora in terms of plasma physics and magnetospheric dynamics, there is something about the phenomenon that invites contemplation of larger questions about our place in the cosmos, about the forces that shape our world, about the connections between things that seem separate. The aurora is, in a very literal sense, a meeting place between the Earth and the Sun, between our planet and its star. Standing beneath it, watching it, is to witness that meeting, to be present at a boundary that is usually invisible. The fact that this phenomenon is happening right now, somewhere on Earth, even as you listen to these words, is itself worth contemplating. At this moment, there are particles striking the atmosphere above the Arctic and Antarctic. There is light being emitted, curtains and arcs forming and dissolving, the auroral ovals glowing faintly or brightly depending on current solar wind conditions. This will still be true tomorrow and the day after, and every day and night for the foreseeable future. The solar wind does not stop. The Earth's magnetic field continues to funnel particles toward the poles. The atmosphere continues to emit light when struck by those particles. The process is as continuous and as reliable as the rotation of the Earth or the orbit of the Earth around the Sun. Some people spend their entire lives at high latitudes and see auroras regularly, dozens or hundreds of times. For them, the aurora becomes a familiar presence, part of the rhythm of the year. During winter, when the nights are long and dark, auroras are common. During summer, when the sun never sets at very high latitudes, auroras still occur but cannot be seen because of the continuous daylight. The people who live in the auroral zones develop a sense for the conditions that produce good displays. The clear, cold nights, the quiet after a snowfall when the air is still and the sky is dark. They learn to read the sky, to recognize the faint glow along the northern horizon that might be the beginning of an auroral arc, to distinguish it from the glow of distant city lights or from clouds catching moonlight. For others, seeing an aurora is a rare or once-in-a-lifetime experience. Someone living at mid-latitudes might see an aurora only during a major geomagnetic storm, an event that occurs perhaps a few times per decade. The aurora they see will be different from those seen regularly at high latitudes, fainter, lower on the horizon, often dominated by red colors because the auroral oval has expanded far enough that they are seeing the high-altitude red oxygen emissions rather than the more common green. But even a faint aurora can be impressive, especially to someone who has never seen one before. The simple fact of seeing light in the sky where no light should be, light that is not from the moon or stars or any human source, can be profound. Photography has made auroras more accessible to people who cannot travel to see them in person. Social media and photo-sharing websites are filled with images of auroras taken by photographers around the world. These images have done much to increase public awareness of and interest in auroras, but they have also, in some ways, created unrealistic expectations. As mentioned earlier, cameras can capture colors and details that are fainter than what the human eye can see. A person standing next to a photographer might see a pale glow while the camera records vivid greens and purples. This does not mean the camera is lying or that the colors are not really there. They are in the sense that photons of those wavelengths are being emitted. But the experience of seeing an aurora with the naked eye is different from seeing a photograph of an aurora, and both are valid ways of experiencing the phenomenon. There is also the question of light pollution, which affects auroral viewing more each year as human development spreads and as outdoor lighting becomes more common and more intense. Auroras can be seen from cities during very strong geomagnetic storms when the aurora is bright enough to overcome the light pollution. But fainter auroras, the kind that occur most nights in the auroral zones, are easily drowned out by artificial light. This means that even people living at high latitudes might have difficulty seeing auroras if they are in or near urban areas. Dark sky preservation, the effort to reduce light pollution and maintain natural darkness, is increasingly recognized as important not just for astronomy, but for the ability to experience natural phenomena like auroras. As our understanding of auroras has deepened, so has our appreciation for their complexity. Every auroral display is unique, determined by the specific conditions in the solar wind, the configuration of the magnetosphere at that moment, the state of the atmosphere. The same location might see dramatically different auroras from one night to the next, even during similar geomagnetic conditions. And within a single display, the aurora is constantly changing, never quite the same from one moment to the next. This variability is part of what makes auroras endlessly fascinating to scientists and observers alike. There is always more to see, more to understand, more to discover. Research on auroras continues at institutions around the world. Scientists use data from ground-based observatories, from all-sky cameras that photograph the entire visible sky continuously throughout the night, from radar systems that can measure winds and electric fields in the ionosphere, and from fleets of satellites that measure conditions in the magnetosphere and solar wind. Some of the most important recent advances have come from multi-point measurements using constellations of satellites that can observe the same region of the magnetosphere from different perspectives simultaneously. These measurements have revealed new details about how energy flows through the magnetosphere and how it is ultimately deposited into the atmosphere to create auroras. There are still many open questions. The exact mechanisms that accelerate particles to the energies needed to create auroras are not fully understood. The relationship between small-scale structures in the aurora, like individual rays or thin filaments of light, and the large-scale dynamics of the magnetosphere is an active area of research. The ways in which auroras on Earth compare to auroras on other planets, and what those comparisons can tell us about planetary magnetospheres in general are being explored as we learn more about the auroras on Jupiter, Saturn, and other worlds. And as our technological infrastructure becomes more dependent on systems that can be affected by space weather, understanding and predicting auroral activity becomes increasingly important from a practical standpoint. But beyond the science, beyond the practical considerations, the aurora remains simply beautiful. It is one of the Earth's great natural spectacles, a phenomenon that combines grandeur and delicacy, power and grace. The fact that it emerges from fundamental physical processes, from the interaction of particles and fields following mathematical laws, does not diminish its beauty. If anything, understanding the processes that create the aurora enhances the experience of watching it, adding layers of meaning to what would otherwise be merely a pretty light show. Knowing that the light you are seeing comes from atoms that were struck by particles that traveled from the sun, that the colors reflect specific energy transitions in oxygen and nitrogen, that the motion is driven by waves and currents flowing through the magnetosphere, all of this enriches the experience. The aurora becomes not just something to look at, but a window into processes and connections that span vast distances and timescales. There is also something humbling about auroras. They remind us that we live on a planet surrounded by space, that we are not separate from the cosmos, but embedded in it. The solar wind that creates auroras is the same solar wind that flows throughout the solar system. The particles striking the Earth's atmosphere during an auroral display are not fundamentally different from particles that have been traversing space since the sun first ignited billions of years ago. Some of those particles might have been part of the sun itself at one time, stripped from its outer atmosphere and launched into space, now colliding with the Earth and creating a moment of light, before being absorbed into the atmosphere, becoming part of our planet. In this way, the aurora is a form of exchange, a mixing of material between the sun and the Earth, one more way in which our planet is connected to its star. As this exploration draws toward its close, it seems fitting to return to where we began, with the simple fact that somewhere right now, auroras are happening. The process continues without pause, without need for human observation or appreciation, driven by forces that operate on scales far beyond our daily experience. The sun sends forth its wind, the Earth's magnetic field channels it, the atmosphere glows. This has been true since long before there were humans to see it, and it will remain true long after humans are gone. The aurora is, in this sense, eternal, or as close to eternal as anything in the universe can be. Stars and planets do not last forever, but for the duration of the Sun's main sequence lifetime, which will continue for another 5 billion years or so. The solar wind will flow and the Earth will have auroras. 5 billion years is an unimaginable span of time. All of human history, from the first stirrings of consciousness to the present moment, spans perhaps 200,000 years at most, a tiny fraction of 1% of the time remaining in the Sun's life. And yet, in that brief span, humans have learned to understand auroras, to predict them with reasonable accuracy, to study them with sophisticated instruments, to photograph them, to travel to see them, and to find in them a source of wonder and beauty. This is, in its own way, remarkable. That a species living on a small planet orbiting an average star in an unremarkable galaxy should develop the capacity to understand the electromagnetic processes that create auroras, to trace the path of particles from the Sun to the Earth, to measure the energy transitions in excited oxygen atoms. All of this represents a significant achievement. And yet, the auroras themselves are indifferent to this achievement. They would continue just the same whether we understood them or not. Perhaps this is part of why auroras are so compelling. They exist at the intersection of the human and the cosmic, small enough that we can comprehend them, large enough that they remind us of our limits. They are beautiful, which connects to something deep in human perception and emotion, but they are also scientific, governed by laws and processes that we can study and quantify. They are accessible. Thousands of people see auroras every year, and millions see photographs of them. But they also remain special, requiring effort and patience and sometimes luck to witness in person. They are part of our planet's natural environment, but they connect us to the Sun and to the larger space environment in which our planet exists. The rhythm of auroras follows patterns that extend beyond individual displays, beyond even the solar cycle. There are seasonal variations in auroral activity that connect to the tilt of the Earth's axis and the geometry of the Earth's magnetic field relative to the Sun. During the equinoxes in March and September, auroral activity tends to be enhanced compared to the solstices in June and December. This effect, known as the Russell-McFerrin effect, occurs because of the way the angle between the Earth's magnetic field and the interplanetary magnetic field changes throughout the year. During the equinoxes, the geometry is more favorable for magnetic reconnection at the boundary of the magnetosphere, allowing more energy from the solar wind to enter the magnetosphere and drive auroral activity. This means that if you are planning to observe auroras, spring and fall offer statistically better chances of seeing active displays than summer or winter, all other factors being equal. Of course, in practice, other factors are rarely equal. Summer at high latitudes brings continuous daylight that makes auroras impossible to see even though they continue to occur. Winter brings long nights that are ideal for viewing, but also brings clouds and storms that can obscure the sky. Spring and fall offer a balance. Reasonably long nights, somewhat better weather than winter in many auroral zones, and the subtle statistical enhancement from the Russell-McFerrin effect. There is also a daily pattern to auroral activity. Auroras are most common and most active around local midnight in the midnight sector of the auroral oval. This is when observers on the ground are positioned on the night side of the Earth, looking along magnetic field lines that connect to the tail of the magnetosphere, where much of the energy driving auroras is stored and released. But auroras can occur at any local time. On the day side, near local noon, there is a separate region of auroral activity driven by different processes, connected to the direct interaction of the solar wind with the dayside magnetosphere. These daytime auroras are generally fainter and more difficult to observe because of sunlight, but they are present, part of the continuous ring of the auroral oval. The patterns repeat with comforting regularity. Each day, each month, each year, the same processes unfold. The solar wind flows, the magnetosphere responds, the auroral oval brightens and dims. The statistical patterns remain consistent even though individual events are unique. This predictability on a large scale, combined with variability on smaller scales, creates a phenomenon that is both reliable and endlessly varied. You know that auroras will occur, but you never know exactly what form they will take, exactly how bright they will be, exactly how they will move. This balance between pattern and surprise is part of what makes aurora watching compelling, part of what brings people back again and again to stand under the dark sky and watch. For those who study auroras professionally, the patterns and statistics are important, tools for understanding the underlying physics and for predicting space weather. For those who simply enjoy watching auroras, the patterns serve a different purpose. They provide structure, markers in time, reasons to look up at certain times of year or certain times of night. They connect individual auroral displays to larger cycles, the turning of seasons, the rhythm of solar activity, the slow drift of the magnetic poles. In this way, auroras become not just isolated events, but part of the ongoing flow of time, part of the larger patterns that structure our experience of the world. In the end, perhaps the most relaxing fact about auroras is simply that they exist, that they will continue to exist, that this beautiful phenomenon unfolds in the polar skies night after night, regardless of human concerns or human presence. There is a comfort in this kind of permanence, in knowing that some things are beyond our control and beyond our influence, that they simply are. The aurora asks nothing of us. It makes no demands. It will shine whether we watch or not, whether we understand it or not, whether we appreciate it or not. And yet, when we do choose to watch, when we do take the time to look up and see the lights moving across the sky, we are rewarded with something extraordinary, something that connects us to forces and processes that operate on scales far beyond the everyday, something that is both scientifically fascinating and aesthetically beautiful, something that invites both understanding and wonder. If you have enjoyed this exploration of auroras, if you have found something in these facts and descriptions that speaks to you, I invite you to stay connected with this channel. There are many more topics to explore in the quiet spaces of the cosmos, many more phenomena that combine scientific depth with the capacity to inspire contemplation and peace. Subscribing to Nebula Nights means joining a community of people who find beauty in understanding, who appreciate the slow, careful examination of the universe and its workings. The like button below this video is a small gesture that helps others find this content, that tells the algorithm that this kind of deep, calm exploration has value. And if you have thoughts or questions or suggestions for future topics, the comments are always open. I read them all, and they often inspire future content. Thank you for spending this time exploring the auroras with me. May your nights be peaceful, your sleep deep, and your dreams filled with the gentle light of the polar skies.